Welcome to the first lecture in thermodynamics. The topics that we will explore in this lecture include an overview of thermodynamics and the energy of a system. In the word thermodynamics, the prefix thermo refers to heat, while the word dynamics refers to motion. Classical thermodynamics began when mankind started to use heat to produce mechanical motion. In particular, the science of thermodynamics grew out of the engineering problem of improving the performance and efficiency of heat engines, such as the steam engine shown here, which utilizes a piston, cylinder, and flywheel design. Classical thermodynamics developed at a time when the structure of atoms and molecules was still unknown, and consequently, thermodynamic laws were empirically derived, that is, derived from direct experimentation. Of course, today we have a very good understanding of the structure of atoms and molecules, and so the laws of thermodynamics are explained by statistical mechanics, which relates the macroscopic laws of thermodynamics to the physical laws governing the motion of individual constituent particles. For now, we can give a simple definition of modern thermodynamics, and we can define it as the science that explains how matter behaves at the macroscopic scale and how this behavior relates to the microscopic scale. Thermodynamics centers on four core concepts, and those are equilibrium, energy, entropy, and free energy. We will explore these concepts in detail during this course. Closely related to these four core concepts are the four laws of thermodynamics, which, recall, are empirical laws. The 0th law of thermodynamics states that thermoequilibrium is a transitive property of systems. That is, if two systems are in thermal equilibrium with a third system, then the two systems are in thermal equilibrium with each other. This is a law that allows us to take a measurable property of a given system and use it to construct a thermometer. The first law of thermodynamics states that the internal energy of a system changes as heat flows in or out of it and as work is done on or by it. In other words, heat and work are two mechanisms that transfer energy into or out of a given system. This can be expressed mathematically by the equation the change in internal energy is equal to heat plus work, where a negative sign indicates a transfer out of the system. This law tells us that the universe plays a zero-sum game. That is, an increase in the internal energy of a system comes at the expense of the energy in the surroundings. For example, the energy that you or I obtain by eating food comes at the expense of plants and animals, which in turn ultimately comes at the expense of the energy from the sun. The second law of thermodynamics states that the entropy of an isolated system never decreases. In fact, an isolated system spontaneously evolves towards thermal equilibrium, which is the state of maximum entropy of a system. This is the law that we wish was not true, because this law predicts the ultimate doom of all life and indeed all physical processes in the universe. The universe as a whole is an isolated system, and so it will eventually reach thermal equilibrium, at which time all life and all processes in the universe will cease. That is, the universe is constantly engineering the eschaton, the time when all life will end. And despite, or perhaps because of the dire consequences of this law, it is generally regarded as one of the most important in all of physics. In the words of the English mathematician, astronomer, and physicist Arthur Eddington, the law that entropy always increases, the second law of thermodynamics, holds, I think, the supreme position among the laws of nature, If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. The third law of thermodynamics states that as the temperature approaches absolute zero, the entropy of a system approaches a constant minimum. And as we will see, while the temperature of a system may approach absolute zero, it will never reach absolute zero. So the framework of thermodynamics is deceptively simple. It is based on only 4 core concepts and 4 empirical laws. And we will begin our study of thermodynamics by examining the concept of energy. Every physical process that occurs in the universe involves energy and energy transfers or transformations. The concept of energy can be applied to mechanical systems without resorting to Newton's laws. In other words, the concept of energy can be used to model and analyze real-world problems. The energy analysis model focuses on a system. A system is a small portion of the universe that is our object of interest. Examples include a single particle or object, a collection of particles or objects, or a region of space. Given a particular system, we then identify the system boundary, which divides the universe into the system and the environment surrounding the system. The system boundary need not be a real surface. For example, I can consider my system, the coffee inside this cup. I can then identify my system boundary as consisting of the surface that coincides with the interior of the cup, together with the imaginary surface that coincides with the surface of the coffee. In other words, imagine the coffee retaining its shape if the coffee cup were removed. This is an example of an open system. An open system has a boundary that allows transfer of both energy and matter, in the form of particles, into or out of the system. A closed system has a boundary that allows transfer of energy, but not matter, into or out of the system. While an isolated system has a boundary that allows neither transfer of energy nor transfer of matter into or out of the system. Now, a very vague but nonetheless common first definition of energy is that energy is the capacity to do work. Now, an important point to keep in mind about work is that work is done on something by something else. And so we will begin by looking at the work done on a system by an agent external to the system exerting a constant force. The work W done on a system by an agent exerting a constant force is the product of the magnitude F of the force, the magnitude delta R of the displacement of the point of application of the force, and cosine theta, where theta is the angle between the force and displacement vectors. Notice that this is an operational definition that tells us how to compute the work done on a system. And notice also that the displacement refers to the displacement of the point of application of the force. However, the applied force need not be the cause of the displacement. Okay, so let's take a closer look at the equation for work. We have that work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of theta, where theta is the angle between the force vector and the displacement vector. You may recognize this as the dot product of the force vector with the displacement vector. Now, if the force vector is perpendicular to the displacement vector. This means that the angle theta is 90 degrees, and so the cosine of theta is 0, and hence the work is 0. Now, if the force vector is parallel to the displacement vector, then either the angle theta is 0 degrees, which means that the force vector is in the same direction as the displacement vector, or theta is 180 degrees, which means that the force vector is in the opposite direction as the displacement vector. So we have two subcases. So if the angle theta is 0 degrees, then cosine of theta is equal to 1. And so the work is equal to the magnitude of the force times the magnitude of the displacement, which is a positive value. That is, positive work is done to the system. And recall that work is a transfer of energy, and so this means that energy is transferred to or into the system. And if the angle theta is 180 degrees, the cosine of theta is -1, and so the work is equal to the negative of the magnitude of the force times the magnitude of the displacement vector, which is a negative value. That is, negative work is done to the system, and this means that energy is transferred out of the system. And of course, if either the magnitude of the force is 0, or the magnitude of the displacement is 0, then the work done on the system is 0. But more generally, for a non-zero displacement, if the product of the force times the cosine of theta, which is the component of the force in the direction of the displacement vector, is positive, then the work done on the system is positive. And in this case, we have an energy transfer into the system. And if the component of the force in the direction of the displacement vector is negative, then the work done on the system is negative, in which case we have an energy transfer out of the system. And so if you only need to know the direction of a transfer of energy in terms of work, then you have simplified equations. So let's quickly talk about the units or unit of work. Force has the unit of newtons, which is indicated with a uppercase letter N. Displacement has the unit of meters, which is indicated with a lowercase letter m. And so work has units of a Newton meter. and this combination occurs often enough that it has a special name. 1 joule, which is indicated with an uppercase letter J, is equal to 1 Newton meter. Now, there are other units that are commonly used in engineering systems, and we will address those later.